Welcome. Today we integrate in polar coordinates. Let me just describe the setup first. So we have a polar coordinates like r, theta, and here are the xy coordinates. Now if we look at a small rectangle here, say we have r maybe between 1 and 2 and maybe theta is between pi 6 and pi 4th, or maybe pi 4th to pi 3rd. So this gives us a rectangle here. Let's call this r. This is a rectangle in polar coordinates, and then we have a map which gives us from this coordinate the xy coordinates, and we know the formula, right? X is equal to r cosine theta and y is equal to r sine theta. That translates us from this coordinate system to this coordinate system. So what happens here, in this case we go between pi 4th and pi 6th, so we go here between pi 4th, theta is pi 4th here, to pi 6th. So maybe like this. And then the radius goes from 1 to 2. So the radius is here 1, radius is equal to 2. And so what happens with this rectangle, it becomes this wedge here. Sector, piece of sector. Now we are interested, obviously this distorts the area, right? Because if you take something here, like if you take something here, kind of closer to it, we get here something with much smaller area. So what happens with this distortion? We want to understand this distortion factor, and we can just look at here. At this area is essentially just the difference between the, let's call this here just dr, and this is d theta. Think about this as something very small here. And then this is equal to dr here, this length doesn't change. And this length here, this is r, this becomes an arc, piece of arc, r times d theta. This is d theta, r times d theta. So what happens is with this area which is here, dA is equal to dr d theta, what happens here, this becomes an area r dr d theta. So there is a distortion factor here which comes from this transformation. So this transformation doesn't preserve area, it makes the area expand if you are far away and shrink if you are close, if you are close by. So let me just explain what we do now when we integrate. When we integrate instead of the x in the xy plane, we integrate in the r theta plane. So integrate in the r theta plane. Just describe the region as it is here, but instead of just writing fxy, so we just write f r cosine theta, r sine theta, and then what we have is the r, this r factor, and then dr d theta. So that's our new dA here, and the only thing we have really to remember here is to include that factor r. Okay, in this first example we want to compute the area of the circle of radius L. You all know the answer, but let's just compute that. In this case, we integrate, we always, most of the time, we start with integrating theta in the outside. So in this case, theta goes from 0 to 2 pi. So that's in the xy, we are here in the xy plane, and that's a standard circle of radius L. And so we go from 0 to 2 pi. Now the radius goes from r goes from 0 to L. Now, because we are computing the area of the circle, we integrate the function 1. That's an important thing we have already seen last time. We integrate 1, we get the area. But now, because of the new coordinates, we have an r here, this integration factor. So let's just do that. In this case, we can integrate the first part. So this is from 0 to 2 pi, and then we get r square half from 0 to L d theta. So this is from 0 to 2 pi L square half d theta, and that's 2 pi L squared, which we all know to be the area of the circle. So let's look at the other example B. Let's take the case when we don't compute the area, but we take the function, the same r here, same region, but we take the function fx y is equal to x squared plus y squared. So in this case, we have we actually compute the moment of inertia of this. So what is this? This is called the moment of inertia, x squared plus y squared dA. And in here also, polar coordinates really does the job from 0 to 2 pi, 0 to L. And then the function in polar coordinates is just r squared. And then still, don't forget the factor r, which we have here, dr d theta. And it's the same computation like before, but instead of r squared, we have just, instead of r, we have r cubed. And r cubed, when we integrate, we get r fourth. So this is equal to r to the fourth from 0 to L. So this is L to the fourth. And so this is 2 pi L to the fourth. So that's the moment of inertia. And then we go into polar coordinates. That's just the integral from 0 to 2 pi. And then we have from 0 to infinity. The radius goes from 0 to infinity. And what happens is this is e to the minus r squared. And then we have that factor r, which we should not forget. So that is something we can integrate, fortunately, because of that r factor here. So this is equal to integral from 0 to 2 pi. And then, so this is just e to the minus r squared over 2. 0 to infinity dt. Just double check if you take the derivative, you get the minus 2r, and that cancels the, and we get the e to the minus r squared. So that's, when we take infinity here, we get 0. When we get 0, we get, so this is the integral from 0 to 2 pi. And when we get 0, we get 1. So this is equal to 1/2 d theta. This is 2 pi half. This is just pi. So this integral is pi. Now, a very nice application of this is in statistics. And let me just explain that. When we take that, we can actually write this a little bit differently. We can write this as the minus infinity to infinity, and then we write this here as e to the minus x squared times e to the minus y squared. Now we can take the e to the minus x squared, e to the minus y squared out, because that's a constant. Minus infinity to infinity, e to the minus x squared dx, and then dy. So that's a little bit a clever way to rearrange that integral. That part was a constant inside here, so I could take it out. But now this part is a constant because this is just a number. We can take this out. So that's the minus infinity to infinity, e to the minus x squared dx, integral minus infinity to infinity, e to the minus y squared dy. And now that's something that you should realize, right? That this integral here is written with respect to y. This is written with respect to x. These integrals are the same because it just matters what kind of variable you're using. So what it actually means is that this product of these two this this is equal to the integral from minus infinity to infinity e to the minus x squared dx squared. So we see a very nice consequence of that computation is that the integral from minus infinity to infinity e to the minus x squared dx is equal to the square root of pi. And that's used in statistics. The reason why we divide by the square root of pi in the normal distribution is that 1 over square root of pi e to the minus x squared is a probability density function. A probability density function is something which is non-negative and which integrates up to 1. Non-negative and integrates up to 1. Pretty cool. One of the most beautiful computations in calculus. Okay, let's look at the setup. We have a surface in space. Which is parametrized by some parameter. Usually we have called this UV, and that's x, y, z. So what happens is this region here is mapped into a surface. And we have parametrized that. That's given by a map R. Now we have also seen that there are grid curves here. Well, these grid curves go here, and there are other grid curves here. Maybe these grid curves here go here. Now we want to understand, in order to compute the area of the surface area of this surface, we want to understand what happens with a little rectangle here. What happens here with this is du, and that's dv. Right? What happens with this area here? So dA is just du dv. What happens with this here on the surface? So let me just make a little bit a bigger picture. So what happens here is this du dv. That goes over into a small parallelepiped on the surface. Let's just move it a little bit up here. So that goes into a parallelepiped. Maybe that's the point UV. That's the point R of UV, which is a point in space. And now we have these grid curves, right? If we just take these grid curves where v is constant, so they go over here into grid curves here. And what happens at this point here, if you differentiate this with respect to u, that's only u is a parameter here. We get a vector which is r of u. So r of u is the derivative, the partial derivative of r with respect to u. Let me just write that down. So r of u, that's xu, yu, zu. So these are functions of u and v which we differentiate with respect to u. So that's a vector tangent to the surface. Let me just write that also here. So this vector here, maybe that's the where we are looking at things. And so this is this vector here. This is ru. And then we can also vary the other vector. We can the other parameter v. And when we vary the other parameter, we get these grid curves here. And then when we take the derivative, we get here rv. So we get rv. And so maybe we take this this little piece here is actually kind of so small here. That's the piece here. That's this piece here. Maybe this piece here. So Ru and Rv are these vectors which we have here. Now we have learned how to compute it. This is essentially a parallelogram here, and we have learned how to compute the area of a parallelogram. But what we have here, if we take Ru, that's the velocity, times du, right? This du, this is kind of like a little time we are traveling. Then this vector here is, let me just write it until here. Maybe I just take it red and green. So this vector here, this vector is then Ru du. So it's the velocity times time, that's the displacement. And here also, that's just this vector here is actually just Rv dv. So now the area of this parallelogram we have learned that this is Ru cross Rv. And then we have also, because we have du and dv, times du dv. Now we call this ds. This is an area element on the surface. And what we do is we integrate that up. That's kind of, think about this as the area of that little piece here. Now when we integrate, we sum up little pieces of area elements. And so what we do is we integrate over that whole region R in the uv plane. We integrate the Ru cross Rv. So that's the surface area. So it's here in the corner, but it's very important. Surface area formula. So it's a nice place where calculus again shines, because it combines derivatives, which we have here, partial derivatives, with integration. Up we have already seen, right, the x, y, z, that's equal to L sinus phi cosine theta, L sine phi sine theta, and L cosine phi. Something you should know by heart. That's a very important parametrization. Now this is, we have to now compute x phi, y phi, z phi. That's the r phi, right? That's one of the things we have to do. So this is L cosine phi cosine theta, L cosine phi sinus theta, and minus L sinus phi. And then we have r theta. That's x theta, y theta, z theta. Now here we get minus L sinus phi sine theta, L sinus phi cosine theta, and 0. And now we take the cross product, r phi cross r theta, and compute the length of it. And I will show that a little bit more in class, but you can do that on your own. You get just L square sine phi. Now the surface area of the sphere is just the integral. We integrate over this region here from 0 to 2 pi. Very nice to have a rectangle, right? 0 to pi. and then we take the L square sine phi. That's the factor, right? That's this L phi cross L theta. And then we have d phi d theta. Now if we integrate sinus phi, we get minus cosine phi at pi and 0. That gives us 2. So this whole thing is 2L square. And then we get 4 pi L square. Which is a computation which already Archimedes did. He was very proud about computing the volume and the surface area of a cylinder. Of course, he did it not like that, but he realized that it's actually the same than the surface area of the cylinder which you have when you put a cylinder, wrap a cylinder around it, right? You've seen the last time the formula. This is L. This is pi L square. No, 2 pi L. 2 pi L is the length, and then times 2 L. So you realize that when you project here a little surface area part onto the cylinder, that this actually preserves area. So instead of computing the surface area of the sphere, we can compute the surface area of the cylinder, which is pretty cool. Doesn't need any integration anymore. So what we want to do is to compute the surface area of this paraboloid here. Now there are two ways to do that. One way is to parametrize this with so what we can write x, y, z as, and then we have a r cosine theta, r sine theta. And then z is equal to r square, right? And now we can do it. So we have, instead of u we have theta, and instead of v we have r. And then we can compute r cross r theta and integrate that from 0 to 2 pi, from 0 to 1 dr d theta. I'm not doing it like that because that's more work. What is actually nicer is to write it directly as a graph, where, because now we have Rx is equal to 1, 0, 2x, and Ry is equal to 0, 1, 2y. And now if you take the cross product now, so Rx cross Ry, then you get the first thing, you get minus 2x. You get here, in the second one you get minus 2y, and in the third one you get 1. So that's the length of this, which is the square root of 1 plus 4x squared plus 4y squared. And so what we have to do is to integrate that over the whole we have to integrate that over the whole disk of radius 1. So what we get is we integrate over this the region R, which we have here, kind of, which maps here. If we just use the usual Cartesian, the usual parameterization like this as a graph, and this is actually our region. This is our region here in the xy plane. So we just reintegrate. This is our region R. So we integrate over this region R, square root of 1 plus 4x squared plus 4y squared dx dy. And now go to polar coordinates. I prefer that than doing this. This is more complicated here with the, so just now go to polar coordinates, and then we have from 0 to 2 pi, 0 to 1, square root of 1 plus 4r squared r dr d theta. And that's easier, and we can do that, and actually you do that in a homework, something like that. So I leave that. Remember surfaces of revolution. So we have r and z and theta. So that was g of z cosine theta, g of z sine theta, and z. That gave us these nice surfaces of revolution where we have something, you know, and the radius, right? The radius here depends on z. That's g of z. Radius depends on z, and then we integrate maybe from z is equal to a to z is equal to b. So I will derive that in class, but if you compute rz cross r theta, you can do that quickly. What we get is the square root of 1 plus g prime z square times g of z. So the surface area in general is then in general we integrate from a to b dz, and then we integrate also theta goes from 0 to 2 pi d theta dz. Just d theta here. And then we have that formula here, square root of 1 plus g prime z square g of z. So that's then just, we can take that out. That's 2 pi integral from a to b square root of 1 plus g prime z square g of z dz. So that's a surface of revolution formula, and we will look at the example of the trumpet. It's a famous example of the trumpet where we have a radius of 1 over z. So g of z is 1 over z. That's the Gabriel trumpet. You might have seen it in single variable calculus, but it's a very nice example where the volume of the trumpet is, you can compute that, the volume, we just compute volumes next week. The volume is equal to pi, but the surface area is given by this formula here. So we have 2 pi, and then we integrate from 1. Let's just see, we have 1, and then the radius is equal to 1 over z. We start from 1 and we go all the way to infinity because it's a heavenly trumpet, right? And then from 1 to infinity, and then we have a 1 square root of 1 plus z prime is minus 1 over z square, 1 over z to the 4, and then 1 over z dz. That's a pretty cool integral. Not so, actually we cannot do that so easily, but we know that this is bigger or equal to 1. So this is bigger or equal to 2 pi, the integral from 1 to infinity, 1 over z dz, which is 2 pi, and then we have the log of z evaluated from 1 to infinity, and that's actually crazy. That's infinity, so that's 2 pi. Yeah, that's infinity. It's an infinite surface area. So the trumpet here has infinite surface area, but it's bigger than something which is infinity, so it's infinite surface area, but finite volume. And the reason why it's so famous is because you can fill it with paint, but you cannot paint it.